Hello everyone, I'm Ridhan V, currently pursuing second year BE in the stream of Electronics and Communication Engineering. As a part of our course assignment, we are now presenting the comparison of AD712 and IC714. Me and my teammates are presenting these topics. Okay, let's move the session. Okay, content wise, we are going to see comparison of AD712 and IC714 pin diagram, input offset voltage, input bias current, voltage noise, sleeve rates, dynamic response, comparative table of AD712 and IC714, advantages and disadvantages, conclusions. Okay. Comparison of AD712 and IC714 pin diagram. AD712 two having two op amps, and two inverting input and two non-inverting input and two output and two power sources, which is VCC and minus VE. Okay, in comparing with IC741, it is having the two op amp. So see the IC741, it is having the only one op amp, one inverting terminal and one non-inverting terminal and one output, but also having the two power sources here and two offset null and one not connected pins are there. Next we are going to see input offset voltage. AD712 having the very low input offset, so it is easy to maintain the precision and reduce the drift. Comparing AD712, IC741 has a higher input offset voltage around 2 millivolts to 6 millivolts, with worse stability over temperature, making it less precise. Comparing AD712, it is a less precise in application requiring high accuracy. Next, input bias current. AD712 offers low output bias current, so and low input offset currents also, with both values specified in warmed up conditions. Typically IC741 has higher input bias current, which can be limited for application needing high input impedance and low current. Next, voltage noise feature here, low voltage noise. AD712 having the low voltage noise comparing with a high voltage noise of IC741. So it is suitable for sensitive signal application. So IC741 more suitable for general purpose applications rather than low noise or sensitive signal applications. Rather than low noise or sensitive signal applications. Next, sleeve rate. Comparing sleeve rate, AD712 having the highest sleeve rate, so it has to handle rapid signal changes. In IC741 having a lower sleeve rate. IC741 having a lower sleeve rate around 0.5 volt per milliseconds. It's a microsecond. Having the 0.5 volt per microsecond. So it limits its performance in fast signal application. Dynamic response, both are the slower response, but it will not suitable for application requiring rapid response. So it application requires rapid response. Okay. Next, comparative table of AD712 and IC741. Input bias current is very low in AD712 comparing with IC741. IC741 has having a higher input bias current. Next, offset voltage. AD712 having the very low offset voltage, but IC741 is very higher. Okay. Noise performance wise, higher noise and less suitable for sensitive application in IC741. Comparing with IC741, AD712 is a low noise suitable for previous circuits. Low noise, so it is suitable for previous circuits. In power consumption wise, we are going to uh, in power consumption wise, it having the lower power consumption, but in AD712 having the moderate, it may be lower or higher. Okay, sleeve rate be 0.5 volt per microseconds. Comparing with IC741, AD712 has 16 volts per microsecond. I confused the micro and milli here, so that's why I'm troubling to say the micro and milli. Okay, sorry. Gain bandwidth product 4 megahertz. It in IC741 having a 1 megahertz. Okay, temperature stability, high stability over a wide temperature range. Okay, moderate stability. Okay, in voltage supply range, plus or minus 4.5 volt to plus or minus 18 volt. It is having the plus or minus 5 volt to plus or minus 18 volt. Application, it is used in precious instruments, low noise designs, general purpose use, less critical designs. Okay, price wise, we are going to see IC741 having the affordable compared with the AD712. AD712 having the higher cost because of there is two op amp, so it having the very high specifications, so that's why. Okay, next we are going to see the advantages and disadvantages. Performance wise, it is very low noise, high precision, fast response in AD712. Comparing A741 advantages: simple, robust and affordable. So what are the disadvantages in the AD712 having the higher cost? In comparing IC741, it has a higher noise, lower precision. So it is opposition of the IC741, right? Okay, flexibility, better for demanding precision application. Okay, widely available, used in non-critical designs. Okay, consumes more power than IC741. Okay, limited performance in high precision torques. Stability wise, excellent stability under varying conditions. Okay, easy to use in basic circuits. What are the disadvantage? It is more complex circuitry. Okay, in IC741 having poorer stability under extreme conditions. Power efficiency, suitable for medium power designs. Okay, IC741 having the lower power consumption in simple tasks. AD712 having the disadvantages of power efficiency, having moderate power consumption. It may be lower or higher. So this is why the very major disadvantages in the power efficiency, right? Okay, limited to basic applications. In IC741 we are limited, we are only use limited power efficiency. Okay, next, we move to next conclusion session. Okay, conclusion we are going to see AD712 outperforms the IC741 in precision. Okay, input bias current, noise, okay, and noise, performance and speed. It is better suited for high precision, okay, and high speed applications such as DAC and ADC buffers. Okay, while IC741 is a basic op-amp. Okay, uh, it remains a popular, uh, cost effective. It may be of cost effective choice for simpler, less demanding tasks. So that's why both are demanding one, but AD712 having the more specifications compared with IC741. So AD712 is the better to use. Okay, next, thank you everyone for this